Hello and welcome to another video. Today we will be learning about polynomial functions and end behavior. So the end behavior of a function is going to describe how a function behaves as it moves infinitely to the right or to the left. In other words, the end behavior is what happens to the values of f of x or your y values as your x's increase or decrease without bound. So all that means is that what happens to your y values as your x's go indefinitely to the right side or the left side. So we have some end behavior and limit notation that we need to learn about. So if we look at this, you will read this as the limit as x approaches negative infinity of f of x, and then you'll say is equal to, and then your answer. This will always be the same for any left behavior of any function, and all it means is as the x values decrease without bound, or like I said, as the x values decrease forever, the y values of x do this. The right end behavior will be similar, the limit as x approaches positive infinity for f of x, or as the x values increase without bound, the y values of f of x approach this number. Let's look at the first example and see if this makes sense. We are going to be looking at the left behavior first, verbally, then we will look at the left behavior limit statement, and then we will do the same thing for the right. So the left side, again, we are focusing on the left side of the graph, and we're saying as my x values decrease without bound, what are my y values doing? If I look at my y values on the far left of my graph, I can see that they're increasing without bound or increasing forever, approaching positive infinity. So verbally, I am going to say as the x values decrease without bound, the y values of f of x increase without bound. So the limit notation will be the limit as x approaches positive infinity for f of x is equal to positive infinity. You can also think of it as having this arrow pointing both to the left and up. So the left side is what's covering the x part, again decreasing without bound or decreasing forever. And then the up arrow describing what the y values are doing, they're increasing, getting larger and larger and larger. Or again, you can say that you're approaching positive infinity. Now let's look at the right side. So as we look at the right side, we notice that again I have an arrow pointing to the right, but it's also pointing down. The right part will be the x values. So as the x values increase this time without bound, the y values of f of x decrease without bound. Again, I can see that my y values will keep on decreasing forever, or I can say the limit as x approaches positive infinity for f of x is equal to negative infinity. Again, the y values will keep on decreasing forever, and that's what the down arrow tells me. Now let's look at B. If we look at this one, we notice that both of them are going up. So for the left side, I'm going to say as the x values decrease without bound, the y values of f of x increase without bound. In limit notation, the limit as x approaches negative infinity for f of x is equal to positive infinity. Again, for the left limit, this is part of your setup, and then this is your actual answer. For the right behavior verbally, I'm going to say as the x values increase without bound, the y values of f of x increase without bound as well. In limit notation, the limit as x approaches positive infinity of f of x is equal to infinity. Like I said before, the right behavior limits, all of them will have the same thing on the left side, and then the right side will be your actual answer. What are my y values doing at that specific point? For example number 2, they want you to sketch a polynomial function with the following end behaviors. So looking at A, they want the limit as x approaches negative infinity for f of x to be negative infinity. So I'm going to put a note here that I'm talking about my left limit, and that I am approaching negative infinity, meaning I have an arrow pointing down. For the second one, this is going to be my right limit and should also be pointing down, because as you notice, both of your limits go towards negative infinity. So I'm just going to do a quick sketch of my graph. And then I'm gonna see on the left side, I should have an arrow pointing down and left. And then on the right side, I should have an arrow pointing right. They look kind of flat. They should be going more towards the left. So if you want to draw a better graph, you can. For this one, they want the limit as x approaches negative infinity to be negative infinity, meaning I have an arrow pointing down. And then for the second one, as x approaches positive infinity, they want the answer to be positive infinity, meaning you have an arrow going up. So I'm going to do a better job on this one to make them look like left and right. So that's a possible answer to that. And then again, you can draw different ones that meet the requirements. So for this one, it could look something like that. For this one, you could have something that looks like that. So again, not just one or two right answers, but multiple answers that you can have. We can use some of the properties of polynomials to figure out their end behavior by just looking at the equation without the need to look at the graph. So this will help us on the non-calculator part of the test. I'm going to give you two different ways to do it. So the first one is by using the leading coefficient, and then if it's an even degree function or an odd degree function. So for this one, the easiest way that you're gonna do this is by looking at the end behavior on the right side first. So if your right side goes to positive infinity, that means you have a leading coefficient that is positive. If the right side goes to negative infinity, that means you have a leading coefficient that is negative. After you figure out the right side, you can look at the left side. So if the left side goes in the same direction as the right side, then you have an even degree function. And if it goes in the opposite direction, then you have an odd degree function. So we can use this information to figure it out. Personally, I like to think of an odd and even function that I already know. So I know I have an even function that I already know, which is y equals x squared. And as you can see, if you remember from your parent functions, I can see both of the arrows going up, or I can look at the leading coefficient and see that it's a positive leading coefficient. And this will always happen to any even degree function with a positive leading coefficient. Both of the arrows will always go up, meaning both the limit from the left and the limit from the right side are going to be equal to positive infinity. If I look at y equals negative x squared, again, it's still an even degree function, but now my leading coefficient is negative. So on this one, it will look something like that. Both the limit as x approaches positive and negative infinity is going to be equal to negative infinity since both of my arrows are pointing up. Now let's look at the odd. So if I have y equals x cubed, again, odd degree function with a positive leading coefficient. Then I can see that the limit as x approaches negative infinity is going to be negative infinity, and the limit as x approaches positive infinity is going to be positive infinity. If I look at the other one, y equals negative x cubed, again, odd degree function with a negative leading coefficient, it will look the opposite. So the limit as x approaches negative infinity will be positive infinity, and the limit as x approaches infinity is going to be negative infinity. This is kind of all that you need to know in order to be able to figure it out. I am going to go over some examples with you to make sure that it makes sense. Example 3a, I have the function f of x equals 4x to the fifth. So fifth, I'm going to make a note that this is an odd degree. And then I'm going to look at the leading coefficient and see that it's 4, so I'm going to say that it's a positive leading coefficient. So I know that since it's odd, it's going to go in opposite directions. And since my leading coefficient is positive, this graph could be used to find my limits because the end behaviors will behave the same. So the left side is pointing left and down, meaning the limit as x approaches negative infinity is going to be negative infinity. So the limit as x approaches negative infinity for f of x is going to be negative infinity. And then going back to the graph for the same picture, the limit as x approaches positive infinity, again, I can see it is increasing without bound. So it's going to be positive infinity. So the limit as x approaches positive infinity for f of x is also positive infinity. Okay, now let's look at b. I see that I have a even polynomial or an even degree polynomial. So I know both of my limits will be the same. And then I see that I have a positive leading coefficient. So again, that will look like a parabola. So I'm just going to draw it here so I don't have to go back. And then both of my limits will be infinity. So the limit as x approaches negative infinity for g of x is equal to positive infinity. For the right, the limit as x approaches positive infinity for g of x is also positive infinity. Let's look at a few more, see if this is making sense. For c, I notice that I have x plus 3 to the 6th power. So I know that if I were to distribute this out and use FOIL multiple times to do it, x to the 6th will be my part of my leading term from here after I expand it. And then don't forget you have your negative 2 in the front. So that will be my leading term, negative 2x to the power of 6. So again, it will look something like this one, same behavior for the left side and the right side. So I'm going to say the limit as x approaches negative infinity. I'm just going to call it f of x is going to be negative infinity, and then same thing for the right. The limit as x approaches infinity for f of x is also going to be negative infinity. Keep in mind that depending on the problem that they give you, you do have to be reading the problem carefully. So on this one, this is my leading term. So this is what I need to be looking at. Odd degree. And then on this one, I have a negative leading coefficient. So again, this is going to look like negative x cubed. So the limit as x approaches negative infinity for h of x is going to be positive infinity. And then for the right side, the limit as x approaches positive infinity for h of x is going to be negative infinity. Here we have a few more examples. So same thing for this one. So odd degree, then negative leading coefficient. So my graph will look exactly like the one on the left, since I do have the same properties for the polynomial. So this limit will be repeated on the answer for E as well. And then for the last one, I am going to have a 2x in the front. And then when I multiply these two, it'll give me a negative x squared. So I'm looking at my leading term to be negative 2x cubed. So again, that will have the same answers as D and E once you write your limits. Don't forget to change the name of your function from h of x to m of x in that case. You can write your limit statements the same thing. Here we just have two more examples, so I'm going to go through them very quickly. First one, even degree function, negative leading coefficient. So again, it's going to look like a negative x squared. So the limit as x approaches negative infinity for f of x is going to be negative infinity. And the limit as x approaches positive infinity for f of x is going to also be negative infinity, since they're both going down. Last problem, I have a odd degree function, and then I have a positive leading coefficient. So again, I know it's going to look like positive x squared. So I'm going to say the limit as x approaches negative infinity for f of x is negative infinity. And the limit as x approaches positive infinity for f of x is positive infinity. Thank you for watching this video. Don't forget to like and subscribe. And thank you for watching. Have a great day.